Here's video 3 for chapter 3. So we left off last time talking about how moles is kind of this middleman. It can let us get from grams all the way to number of atoms or molecules, so that if you have a sample on a scale, you can then calculate how many atoms or molecules are in that sample. So first, let's talk about this first conversion right here between grams and moles. So to convert grams to moles or moles to grams, we're going to always look for the molar mass, which comes from the periodic table. And we can set up a conversion factor with 1 mole equaling the molar mass. Here's an example. What is the mass in grams of 4.50 moles of potassium? So we start with our moles, 4.50. We automatically bring moles of K to the bottom, and then we put grams on top. We can always convert between grams and moles. We know that 1 mole of any atom or 1 mole of any compound is equal to its mass from the periodic table. So potassium is 39.10 grams. So we multiply the tops and we get 176. I went with 3 sig figs because that's what our original amount was. Similarly, it says how many moles of calcium are in 78.9 grams of calcium. So we start with grams. This time grams goes to the bottom and we can put moles on top. So remember, 1 mole again has the grams on the periodic table. So 40.08 goes on the bottom this time. So we divide and we get 1.97. How many moles of sodium bicarbonate, which formula is given here, are in 508 grams? So again, we start with grams. Immediately grams has to go to the bottom, and we can go grams directly to moles. So 1 mole is equal to this added up on the periodic table. So we added 1 sodium, 1 hydrogen, 1 carbon, 3 oxygens. So that gave us the 84.01. We divide by that and we get 6.05. What is the mass in grams of 6.33 moles of sodium bicarbonate? So we've got our moles this time. Moles goes to the bottom and molar mass comes to the top with grams. So we multiply in this scenario. So be sure to always set this up to show your work, and it'll help you to decide whether to multiply or divide by the molar mass. Now here's a 2-step problem where we're going to do the 2 jumps that we saw up above. So here, if we're starting with grams of nitric acid, the only thing you can do with grams is go to moles. You can just go ahead and keep that in your brain. So grams has to go to moles before it does anything else. So I'm going to bring grams to the bottom, convert to moles. Remember, grams to moles is always the molar mass. So we went to the periodic table and added up H, N, and 3 O's. And then moles is at the top, and so that will come down here to the bottom. And I can then use Avogadro's number to go moles over to molecules. So in 1 mole of HNO3, there are 6.02 times 10 to the 23rd nitric acid molecules. So we have 2 steps here. We first used molar mass to get to moles. We then used Avogadro's number to get to individual molecules. So we multiply everything on the top, divide by the bottom, and here's our final answer. Find the mass of a sample of 2.50 times 10 to the 25th water molecules. So this time we're starting with molecules, which means on the bottom of my first conversion factor has to go molecules. And we know that we can go from molecules, which is like number of pieces, to moles first, using Avogadro. So we can get to 1 mole of water equals 6.02 times 10 to the 23rd. That cancels out molecules. We're in moles. So moles will come to the bottom, and we can go directly from moles to grams using the molar mass. So that came from the periodic table. Multiply, divide, and here we go. So you want to be able to go back and forth a good bit between these steps. So empirical formula, we've mentioned this last chapter, but an empirical formula is the simplest ratio of atoms in a compound. So you can look back to chapter 2 if that seems a little bit fuzzy. But for example, H2O2 is hydrogen peroxide. That's his molecular formula, but it can be simplified to just HO, and that would be called its empirical formula. So here we're going to look at problems of how to come up with an empirical formula. You're always pretty much going to use these same steps. So a lot of times you're given either mass percentage of the elements in a compound, or you're given grams, okay? If you start with mass percent, what you want to do is assume a 100-gram sample. So if you make up 50% of the mass, then you would be 50 grams in that sample. So your percentage can just be changed to grams. And then what did we say we can always do with grams? The only thing really we can do is go grams to moles. Grams to moles will always use the molar mass on the periodic table. And then we look at a ratio of moles, and I'll talk about that here in a second. So here's an example, PABA. You've probably seen this on sunscreen. So it's composed of carbon, which is 61% of its mass, hydrogen, which is 5%, nitrogen 10%, and oxygen 23%. So we know that the formula is going to be made up of C's, H's, N's, and O's. What we're trying to determine is what this simplest ratio is, so what these subscripts are. So up above, we talked about how we take the percentages, and we assume that we have 100 grams of this sample. If we have 100 grams of the sample, then all of these percentages would be the same thing as grams. So we just switch out the percent for grams, and then we do what we know to do with grams, which is go to moles. So I use the molar mass to go grams to moles, grams to moles, grams to moles, grams to moles. You can pause and, of course, work this out yourself. So we get to moles here of each element. This is the mole to mole ratio, but it's just not a clear-cut whole number ratio. So what we do to get that is the next step is always to divide by the smallest moles. So you find which of these values is the lowest, which is the 0.7, and you divide all of them by 0.7, and you will come out with numbers that are very close to whole numbers. So it gives me a really nice ratio, 7, 7, 1, and 2. Then I can put those in as subscripts. And there's my empirical formula. Here again, it's going to be the same steps. There will be just one additional one in this scenario. This time we're looking for a compound that has C's, H's, N's, and O's. So we've got the percentages, and I went ahead and took the percentages and just made them grams, assuming a 100-gram sample. I once again went grams to moles, grams to moles, grams to moles. That's all we know to do. We get to our moles, and the next step is divide by the smallest. We want to divide by the smallest so that we can see a clear ratio. Now I said you would get things close to whole numbers. There are a couple of other options you might run into. Here you got whole numbers, but then you got a 1.5. 1.5 is not close to a whole number, so you can't just round that to 1 or to 2. You got to keep it. So in order to get rid of this decimal, we've got to multiply this by a number that gets to a whole number. Well, 1.5 times 2 will give you a whole number. But if we multiply this guy by 2, we've got to multiply all of them, because this was the correct ratio. So we multiply them all by 2, and here are our final subscripts. A couple of other scenarios you can run into is if you get a 0.25, then you're going to need to multiply by 4. If you get a 0.33, you'll multiply by 3. Or a 0.66, you'll multiply by 3. If you get something that is not really close to one of these, then you have probably done something wrong. So it should either be whole numbers, should be 0.25, 0.33, 0.5, or 0.66. Those are the different options. And there are, I just skipped over it, but there are several examples here that you can practice with the answers given. To then jump from the empirical to the molecular formula. So remember, empirical is the simplest ratio. Molecular is what the actual compound looks like. You have to be given one additional piece of information, which is the molar mass of the compound, of the real molecular compound. So here it says, what is the molecular formula for a compound that has the empirical formula of HCO2 and a molar mass of 90? So here's the deal. If this is the empirical formula, well, it also could be the molecular. Sometimes they're the same. Or it could be double, meaning it could be H2, C2, O4. It could be tripled, H3, C3, O6. Those are all options. You could quadruple it. So it could be any multiple of this guy. So what we're wanting to do is use this molar mass of the real compound and compare it to the empirical. So the way we do this, I've written here, is you take the molar mass of the molecular, which has to be given to you. because that's a mystery. So that's 90. And then you calculate the molar mass of your empirical. So I just went and added up 1 H, 1 C, and 2 O's. And I got 45. So you take the 90, put it over 45. You can already see that this is twice. The molar mass of the molecular is twice that of the empirical. So I get a 2 here, which means I need to multiply all of the subscripts by 2. So H2C2O4 is the molecular. Here's one more. You have an empirical formula of C2H4O. Molar mass is 88. So you take your 88, that's the real thing. You go add up your empirical and you compare. Well, your empirical is 44, so you need to double it again, and it's going to be C4H8O2.